So, so chapter 7, we are talking about fluid flowing pipes. So, katong mga niagi nga mga chapters, naghisguta to, katong chapter 6 is naghisguta to sa how to measure the flow measurement. Diba? Mao na itong gihisgutan. So karon kay bao naman ta sa flow measurement, ato na po i-consider karon ang mga principles sa fluid flow in pipes. So kibale sa chapter 6 we discuss about how to measure the flow in pipes and channels. So katong sa wears, sa orifice. So dito sa chapter 7 we will be talking only about pipes. So pipes are closed conduits, so through which fluids or gas flows. So conduits may be flow or partially full. So pipes are referred to as conduits, so which flow full. So dapat full siya. Kaya nga naman, if it will be partially full, so meaning, like example na to is sewers, di ba? Sewers is nara dire ang tubig. Although circular siya, di siya na to i-consider as pipe, but we consider that as open channel. If there is an opening, if it is partially full, okay? So if it is fully full, example na kanang mga tubo padung sa bahay, di ba? Ang tubig ana is ijang gikuan ang whole nga cross section sa pipe. So mo na mo consider na to siya ani nga chapter. So fluid flows in pipes may be steady or unsteady. So kay bao naman tas definition sa steady. So there are two types of flow that exist. It could be laminar or turbulent. So sa steady flow na siya. So unsa man ang laminar flow? So maghisgutanig karon og Reynolds number. So for it to be considered as laminar flow, the Reynolds number must be less than 2000. So in other books, Reynolds numbers should be lesser than 2100 in other books. So ngali sa gilisan niya 2000. So again, it will be considered as laminar if its Reynolds number is less than 2100 or 2000. So unsay pasabot ana? Di ba kung ko tag kuan steady flow, if this is your pipe, each particle, kung mao ni ang particle sa fluid, mudagan na sa gikan diri pa straight ra. Na kailang particle pa straight. Ang unsteady, ang kalahian sa steady ug unsteady, kani ang particle mo yana. Then na kailang particle mo yana. So magingananag ang imong particle. So dili siya ma-consider nimo as steady. So mo na kalahian ilang duha. So sa turbulent flow is if it exceeds 2000 or 2100, depende sa libro. So atong i-assume nga 2100. So if the Reynolds number is greater than 2100, then you can call that as the turbulent flow. So laminar flow in circular pipes can be maintained up to values of Reynolds number as high as 50,000 if it is in circular pipes. Pero it is unstable, so usually di na siya ma-achieve. So critical velocity is when your Reynolds number is equal to 2000 or 2100 in our case. So if Reynolds number is equal to 2100, so meaning it is critical flow. Nganong critical man? Gamayng dugang ra sa imong velocity, your Reynolds number will become turbulent, di ba? So it is the tipping point from either turbulent or laminar. So mo na atong gitawag na siya og critical velocity. So mo na kalahian. So unsa din ang Reynolds number? So it is a dimensionless value which is the ratio of the inertia force to the viscous force. So mo ni ang formula. So Reynolds number is equal to the mean velocity kani. So velocity times the diameter of the pipe, then times the density over the absolute dynamic viscosity. Or it could be kay bao man ta nga kani. So kinematic viscosity is equal to absolute dynamic viscosity over density. So your Reynolds number can also be this formula. So the velocity times diameter over the kinematic viscosity. So this is for pipes flowing in full. So meaning mao ni atong i-considera. So di na niya ito i-consider kay for non-circular pipes we will only consider this one. So pero if it is a non-circular pipe, so meaning na kay elliptoid, so mura nga nagporma or sa magani nga pipe, so mo ni mo i-consider nga value sa Reynolds number. So you have here the temperature of water. So the density of water in such temperature. So if you notice, basi wala na ito na-discuss sa una or ninjo. So the temperature, as the temperature increases, the density will decrease. It's normal. So nga na, then mao po na imong mu and kinematic viscosity. So mao na. So okay, so the equation for velocity profile for laminar flow is this one. So it could be rewritten as this value. So U is equal to Vc times 1 minus R squared over R sub O squared. So what's the difference between the R? So if karing R nga R is if you consider the radius ani gikan ani padong sa point of sa imong point sa imong particle nga i-consider. Kaya di ba atong gihisgutan ganina is nani tagsa nga particle i-consider. So mao na siya. So di lang kay di man po ni kadyo magamit nga formula. So this is for turbulent flow. Kani di po ni kadyo magamit. So sa shearing stress in pipe, so sa shear stress in pipe, shear at the center is equal to 0. So always remember that. Then as it goes towards the walls of the pipe, it increases, di ba? So kibali kung ano yung pipe nga kuan, so magkanaman na siya kalayo sa center, magkanaman na mo kadako ang imong shear stress. So ang maximum nimo nga shear stress is na dire. Di ba? Kay moment kibali ni inanaman mo kadako imong shear with respect to its distance from the center. So always remember, kay nganong zero man ang center, kay tungod wa man kay friction nga moy-act sa imong kuan. So wa kibali shear nga mahitabo with respect to the wall of the pipe and the water nganing flow. So mo na. So okay. Mao ni kasagarang magamit ng formula gamma HL over 2L X. So it could be also used kani friction factor over 8. So V squared of friction factor. Friction factor will be taken with respect to the Reynolds number. So ato lang i-discuss niya. So kanto, so panagsama pud gamito ng shear stress sa pipe. Usually gamito ni ang shear stress, pagitaon ni shear stress sa pipe. Di ba ning agi man ta sa fluid mechanics nga katong walls, di ba? Katong mga topic sa walls, katong spherical walls. So kato ang imong gamiton nga shear velocity, shear stress, nga ang imong makuha nga shear stress dire mao tong gamiton nimong value sa katong formula ani. Katong so tayo for basta kato mo to kato sa chapter 3, last topic sa chapter 3. So kato nga topic, so ang kato imo makuha nga shear stress dire mao toy gamiton nimo nga re. Kay ngano importante man ni shear stress. So there are times nga mubuto ang imong pipes, especially if high pressure na siya, kay tungod ang imong pipe is di naka-carry sa pressure. So the material failure siya. So dapat nimo i-consider pod ang capacity or ang strength sa imong pipe in order for it to carry the pressure. So makadako pressure, makadako ang imong pong shear stress. So mo na sila. So head losses in pipe. So na kay major head loss ug na po kay minor head loss. So the major head loss, so which is caused by the friction along the straight sections. So kibali, if this is your pipe, if dira nagflow imong tubig, di ba? Since it is a heterogeneous material, mao ni imong flow, mao ni imong fluid, mao po ni imong wall. So there is a friction nga mahitabo. Kung ato nang padak-on, mao ni ang na diri ang tubig, ang imong tubig ni flow dire, the surface of the water with the pipe is na kay siya friction. Kay di ba? Kay ba man sa friction nga mo counter siya sa direction sa flow. If this is the direction of your flow, ang friction is pabalik. So, if mas taas imong pipe, so if mas taas ang length sa imong pipe, mas dako imong friction. So mo nang gi-consider ni nato nga major nga head loss. So ang minor head loss pod is imong gi-consider siya because of the changes in velocity or directions of the flow. So it is commonly expressed in kinetic energy. So mo nang katong kinetic energy is v squared over 2g, di ba? Mo man natong kinetic energy. So we usually express that in kinetic energy, so we just multiply that with constant for it to become a minor head loss. So if we talk about major head loss, mo man taas na topic dire, it acts depende sa diameter and the uniform roughness of the pipe. So meaning, di ba your pipe is composed of materials, depende yung material. So if we have concrete, di ba, na kay concrete pipes, na kay GI pipe, na po kay PVC pipe, etc. etc. So mas hamis ang imong wall sa imong pipe, mas gamay dyan friction factor. So mo na ikalayan nilang duha. So mas rough siya, mas dako siya friction factor. Mo bitaw nga na changes na dyan because the material used in the piping system, even in our homes, changes over time. Remember, we were using GI pipes maybe two decades ago or 3 decades ago. Then we changed from GI pipes to PVC pipe. Then again, we changed from PVC pipe to another kind of pipe today. So lain na nga pipe atong gigamit karon kanang blue, di na PVC siya nga pipe, lain na siya nga material. So masamis pa jud na siya sa PVC. Why is there changes? Because we want to minimize the major head loss, to minimize the friction factor. So mo na siya. Kay for example, katong GI pipe sa una, although hamis na siya og kuan, hamis na siya og inner nga diameter sa iyang inner nga wall, ang diferensya is kusog siya makapilit sa mga silt. So kung imong tanawon tong mga old nga mga GI pipes, mura na nagsiminto ang nasa kilid ana niya. So meaning over time it became rough. So mabitaw na nga as much as possible you have to change your pipes 10 to 15 years, every 10 to 15 years to minimize the head loss and also to clean the water. Kay usually silted na kadyo mong pipe, so inigagi sa tubig, mas paglimpyo sa tubig na may times nga ang mga katong mga silt is inigkuan, so musod gihapon sa imong water system. So mo na yung major head loss. So you have that as HF. So there are 3. So you have Darcy-Weisbach. You also have Manning's formula kane, and also the Hazen-Williams nga formula. So unsay kalahian nila? So there is Darcy-Weisbach, we consider a pipe friction equation. So we will be using the friction factor F. So meaning the friction with respect to the material and the flow. So here the formula head loss is equal to FL V squared over 2G times D kane. So for non-circular pipe we are going to use D is equal to 4R, where R is the hydraulic radius. So kana. Okay, so what we will be using this one, and also we can use this formula 0.0826 FL Q squared over D to the 5th. It is the same with this one. So here for laminar flow we can use F if the friction factor is not given. but you can find the Reynolds number. So you can use the formula F is equal to 64 over Reynolds number, or substituting the formula for Reynolds number, it will become mu over velocity d times the density. So kani. So that is for laminar flows. And for turbulent flows, kani yung mga formula depende sa imong sa imong Reynolds number. So for turbulent flow in smooth and rough pipes, universal resistance laws can be derived. So usually mao ni ang gigamit 8 Vs squared over V squared. So where Vs is the shear velocity, katong nakuha nimo sa shear stress ganina, kani nga formula kani katong V over square root of F over 8. So for smooth pipes, Reynolds number is between 3,000 and 100,000. So so for smooth pipes with Reynolds number up to 3 million, so you are going to use the logarithmic equation 2 log Reynolds number square root of F minus 0.8 and so on. So kana. Pero usually di man siya gigamit. So mao to. Then we also have the Manning's formula. So Manning's formula for the velocity is 1 over nr to the 2/3 s to the 1/2, where r is the hydraulic radius. So s is the slope. So usually this formula kani is used in the open channel. Kani. So see, best known for open channels. But still it can be used for common pipes. Kani magamit gyapon ni siya. So kani. This is what we usually use. So 10.29 n squared LQ squared to the over d to the 16 over 3. So this is the head loss, where n is the Manning's coefficient. Okay, so kani ang mga value sa Manning's coefficient. So depende. So ang kalahian sa Manning formula o sa friction, katong ka Darcy-Weisbach is katong sa Darcy-Weisbach is nag-consider siya sa friction with respect to the material of the pipe and the flow, the liquid nganing flow sa imong system. Whereas sa kaning Manning's formula is gi-consider is ang material nga gigamit sa kuan. So if you notice, here you have your N. So the nature of the surface, so it could be cement surface, wood stave pipe, flank flumes, metal flumes, concrete, precast, cement mortar, cast iron, etc. etc. So mo na yung mga minimum values o maximum values. So for example, if the question is the pipe is used is cast iron, that is new, so you are going to use 0.013. So if it is old, it becomes 0.017. So depende siya. So mo na yung kasagaran nga gigamit, pero again usually n will be given. So again, ang kalahian sa Manning's formula and the friction factor is this one is the using roughness coefficient with respect to the material, kung sa material gigamit, whereas kani is with respect to the friction factor. So the last is the Hazen-Williams formula. So it is usually used in waterworks industry. So this formula is applicable only to the flow of water in pipes larger than 50 mm in diameter. So and velocity is less than 3 meter per second. So this formula was designed for flow in both pipes and open channels, but is more commonly used in pipes. So kani ang formula kasagaran gigamit for Q, and for the head loss is kani 10.67, but some other books mo like 10.9 kalimot ko ani murag nay kalahian, pero this kani atong gamiton for sure. So 10.67 LQ to the 1.85, C to the 1.85, D to the 4.87. So you have here the formula for the values for C, the Hazen-Williams coefficient. So mao gyapon mura sa with respect to the pipe, kung sa nga pipe imong gigamit. So if it is smooth and straight, you have 140. So cast iron and some years in service, so 100. So cast iron in bad condition, 80, etc. etc. So mo ni ang mga values sa imong C1 sa Hazen-Williams. So pari-pariha rin siya sa Manning's formula, but kalahian lang is na siya distinct nga use. It should be large, the pipe must be larger than 50 mm and the velocity must be less than 3 meter per second. So mo nang gamit sa Hazen-Williams. Pero hagdi lang kay kasagaran sa mga problem, moingon man nga use Hazen-Williams or use Darcy-Weisbach or use Manning's formula. Or mabantayan na ninyo if ang given is N, therefore Manning's formula. If given is C, therefore Hazen-Williams, or if given is F, therefore it is Darcy-Weisbach. Or if nakay pangkuha Reynolds number dire, or nakagihisgot nga cast iron pipe or unsa nga material nga gigamit, so it could be N or C, but in C you can determine that with kaning nga mga parameters niya. So minor head loss, as what I have told earlier, it is with respect to the kinetic energy, so kV squared over 2G. Mao ra jud ni kasagaran nga formula nga gigamit. So if you notice this one, if there is sudden enlargement, so when we talk about sudden enlargement, anam og kadako imong pipe og kali. So di ba? So if mudako imong pipe ani dako imong area, ang mahitabo imong velocity is decrease. Di ba? From dako nga velocity to gamay nga velocity. So here V sub 1 is before enlargement, then V sub 2 is the after enlargement. So dako minus gamay over 2G. So mo ni imong head loss. So we only use this one. So then for gradual enlargement, you have there the K, so the coefficient of K. So this one, it will be used with respect to the ratio between the area sa ikaduha sa dako sa mingdako nga side over sa minggamay nga side. So this one here is the angle. So for example, if the angle nga increase niya is 20 degrees, so we move into this ato inaon lang nga 40 degrees. So if we have this, the value aning angle is 40 degrees, so we go into this aning side. Then if mudako, imo pangitaon ang imong value sa imong area 2 over area 1. If it is greater than 4 but less than let's say 2, so it should be somewhere here. So if it is somewhere here, so imo i-connect atong supposedly this will have interpolation. So if kani mao ni imong value sa k, it will become 1. So gikan sa 40 degrees padung sa ka, then kani 1. So if it is let's say 2 and 1, so kani nga values ani, so pwede na dire, then 40 degrees, so nasa dire, so it could be 0.75. So imo ra na siya kuhaon kani nga line padung sa ka ato inaon nga katong ganina, ato inaon nga 3.75 ang A2 over A1, so kani ang value nga makuha nimo. Kay bali kaning mga curves, kaning tulo ka curves is the ratio between area 2 ug area 1. So mo ni mahitabo. So ingani. So imong kwaon if asa siya mingsod. If mingsod siya ani, so nasa dire. If mingsod siya with respect ani nga duha ka mga boundary, so basig na siya dire. So 0.75 or something. Kung 70% pod, 70 degrees rather, so na dire. So pwede mo 1.1, 1.2. So ingana pagkuha nimo sa K. Sa value sa K. So sa sudden contraction pod, so meaning gikan sa dako ming binali sa katong A. So the head loss M across a sudden contraction of a pipe. So if you notice K V squared over 2G, this one is V squared over 2G. This one is also V squared over 2G. So kinetic energy reduced siya tanan. So Kc is from table 7-5. So with respect to the diameter na po din siya. So if you divide both the diameter, so makuha nimo kita ay gikan sa 250 mm over 150 mm. So kibali mo na yung diameter sa pipe. So ang answer ana which is 1. D2. So nasayop. So it should be 150. Okay. 150 over 250 kay D2 means na dire. So this is 150, this is 250. So 150 over 250, answer na is 0.6. So 0.6, so imong Kc gagamiton is 0.28. So ato inaon nga 0.28 times V squared over 2G. Again, this is if it is sudden contraction. Moingon mo po ng problem nga there's a sudden contraction nga na, so mao ni nga table imong gamiton. So there are special cases of sudden contraction is the entrance loss for pipes connected to a reservoir. For this case, the value of Kc as follows. So kani. Then bends and standard fittings. If there are bends, so kibali, di ba naman kay 45 degrees, na kay 60 degrees kani mga bends nimo. So napo kay napo kay minor losses ana. So K, the value of K, so that is L over D. So if it is fully open, if the angle valve is fully open, close return bend. So naragya po ni mga descriptions sa mga fittings. Then this is the value of your K with respect to your L over D. So increasing pipe length using L over D. Okay, so muna. Okay, so mo to ang mga major losses and minor losses. So karon you don't need to memorize anything, but in the board exam you have to memorize everything. Kani. Then don't worry kay sa board exam you will be given this mga graph. So for example kani nga graph makuha nimo ang Reynolds number, di ba? Then kani is mga diameters. So makuha nimo ang friction factor, values of friction factor. So ingana. So kibali ka mo ipakuhaon sa mga values. So katagaan mo napo ni graph ning sa Hazen Williams, wa laman dire. So okay. So pipe discharging from a reservoir. So if this is your reservoir, so I think we have discussed this already. So remember that if we consider an open reservoir, ang naara dire is P over gamma ra. Okay? So this will be in static. Delete P over gamma. Actually, ang naara nimo dire is ang Z. So with respect sa imong datum, that is Z, your P over gamma is equal to 0 if it is open. Then your V squared over 2G is also 0 if it is in a reservoir. So kana if this is your condition, if you notice diri nga part sa reservoir H ray naa wa kay P over gamma o V squared over 2G. Kay in a reservoir, it is in static. So if this is your pipe, if you have here your piezometer, so sa pipe, there is a head loss here, minor loss, katong ganina nga atong gihisgutan. So, ang mahitabuan na, since flowing naman imong tubig dire, di ba? If you put piezometer here, ang imong tubig will be up to here. Kay piezometer man mo gigamit. But if you put a pitot tube here, ang imong flow is na dire. So mo na kalayan sa duha sa pitot tube ug sa piezometer, di ba? So instead of your head having in this height, dire ra ang resulta kay tungod na kay head loss. So there is already head loss in the entrance, di ba? And also you have a head loss because of friction factor. Okay? So meaning if you are going to draw the hydraulic grade line in the pipe from reservoir to a pipe to the exit, usually to make it simple, dinagayin ko mo inga ng head loss dira, diretso ra ko gikan dire padung nako inga na, di ba? Usually katong kuan sa last chapter 5, inga na hon drawingan sa hydraulic grade line. So anong gituyo nga inga na kay simple wa pa man gi-consider mga head loss, pero if you have to determine the exact drawing, so mo ni ang exact na drawing. So napakay sudden minor losses at the exit of the reservoir, so padung nga na. So mo nang value. So kanang EGL nimo na kay V squared over 2G, this is the mahibaw-an nimo ang distance sa imong flow paggawas. Okay? So ni paggawas ani dya. So kana makuha nimo V squared over 2G. So if it is a pipe connecting to reservoir, the head loss is equal to H is equal to head loss, minor head loss and the major head loss. So you have here the minor losses, so sa entrance ug sa exit, and also the head loss of with respect to the major loss kaning sa imong pipe. So the total head loss kani is equal to summation of the two. So the principle in the pipes, so na kay 3 ani, you have pipes in series, pipes in parallel, and equivalent pipe. So when we talk about pipe in series, if you notice kani, di ba ang imong pipe is connected. Ang tulo ka pipe is connected. So according to continuity equation, there's no energy added or energy loss during the system. So it means nga ang imong Q1 must be equal to Q2 must be equal to Q3. Okay? Kung unsa na to mingsod, mao na jud po to amo gawas. Mao na ang imong continuity equation, mao na imong energy, mao na imong flow. But here in the head loss, nagkarenay nag-value imong mga head loss. Now nagkarenay nag-value imong head loss. Atong tanawon ang major loss. Look at the formula for the major losses. Na kay diameter, na po kay length, di ba? Itong erison. So na kay diameter, na po kay length. So kanang diameter ug length in the pipe in series, magkalain-lain na silang values. Here. So it could be that the pipe 1 is longer than pipe 2 and pipe 2 is shorter than pipe 3 or whatsoever. So meaning with that, naapektuhan imong head loss. And also the diameter. So mas gamay si pipe 1 ni pipe 3, mas gamay si pipe 2 ni pipe 1. So mo na nahitabo dire. So mo na ang mahitabo po sa imong head loss. So nasa jay lain-lain nga value sa imong head loss. Okay? So meaning that the total head loss kani is equal to the summation of head loss 1, head loss 2, head loss 3, and also the minor losses. Nama kay minor losses dire kani. This is minor losses. Okay? Ngano minor losses man? Sudden contraction, sudden enlargement. Okay? So na kay mga minor losses. So usually di po na i-consider sa ubang problems, dili consider ang mga minor losses. Ang major losses ra i-consider. So kani, if pipeline in any problem is about 500 diameters, the error resulting from the neglecting will ordinarily not exceed 5%, and if the pipe length is 1000 diameters or more, the effect of minor losses can usually be considered as negligible. So when it is negligible, wa na kay minor loss nga consider. Okay? So the difference between pipe in series and pipe in parallel is look at the equation for discharge. Q1 is equal to Q2 is equal to Q3 is equal to Q. But in here, Q, the total discharge, ato yun ni QT, is equal to Q1 plus Q2 plus Q3. Why Q1 plus Q2 plus Q3? Look at this diagram. Unsa tong gingon ninyo ganina? Kung unsa to aming sod, mao po to mo equal sa mugawas. So meaning, ang kaning Q ni mo dire is nabahin ka tulo. So if imo nang i-add ning tulo, equals ni siya ni Q. Okay? So mo na siya ang nahitabo dire. But if we consider in this pipe, your Q will be minimized. Meaning, ang kanimong mga Q dire is mabahin siya ratio in proportion with respect to the length and the diameter. So meaning, wa nagpasabot nga naa ni taas si Q, kaning si Q1, mas gamay ni siya discharge. Possible mas taas ni siya discharge gapon if it is shorter pipe, di ba? If it is shorter pipe, if consider nimo ang 2 ug 3 kitay mas gamay ni siya ato na 100 meter ni kani is 1000 po ni, etc. etc. So, ang mahitabuan na mas taas ni discharge ning Q1 kaysa ni Q2, Q3. In some sense. So meaning kung kani mo i-consider dire kani kung imo ni siya i-consider dire ang imong head loss 1 must be equal to head loss 2 must be equal to head loss 3. Okay? So mo ni mahitabo. Ngano mahitabo man ang iyana? Because the value that is the value of the discharge distributed to Q3 and Q2 will be rounded off or will be taken from the value of Q1 with respect to their diameter and their length. Okay? So na siya ratio ni siya, so imo ma-consider nga usa ra jud imong head loss ana nga dapita. Di man pareha dire nga lain-lain usa ra jud kadaganan ni Q, so mao na nga imong head loss is magkalain-lain. Pero dire ang imong Q is mabahin siya with respect to the head loss. So mao na nga mas masabtan ni nato sa equivalent pipe. So sa continuity equation, ma-consider gyapon siya kay if you look in this diagram, kaning Q1 nimo dire nabahin siya Q2 into Q3, pero at this point nag-converge na po sila mahimong Q4. In this equation, you have Q1 is equal to Q4. Meaning there's still energy nga wa gyapon energy nga na loss. So na gyapon conservation of energy. So nakuha na to gikan sa pipes in parallel nga si Q1 is equal to Q2 plus Q3. Diba? Or it could be also Q2 plus Q3 is equal to Q4. Kaya di ba, pagpadunin mo dire, pila may value sa Q4, Q2 plus Q3. So, head loss HF2, HF3 is equal because we know that these two are parallel. Okay? So, therefore, the head loss total kani is equal to HF1 plus HF2 plus HF4 or HF1 plus HF3 plus HF4. Okay? So, kana. Kibali, ang kaning HF2 pwede mabaylo-baylo ani. So always remember that the number of equations needed to solve the problem must be equal to the number of pipes. You have here 1, 2, 3, 4. So you must have 4 equations also. Unsa to ang giingon ganina? Equivalent pipe. So, kaning tulo ka pipes, for example, gigamuhan na kang anong nay tulo ka pipes, imong gusto is alid ang usa ka pipe tanan. So, instead of using this one, we are going to use this one. Take note that the head loss must be equal to the original. So, meaning, ang head loss ani must be equal to the head loss ani. And also the discharge must be also equal. Okay? So mo na yung kuan si ani. So kibali ang kaning siyang duha dire, there is an equivalent pipe nga posibleng buhaton nimo. Pero there must also be equal to usa ka head loss. So na may uban nga problem nga mayon nga okay, there is a parallel pipe here. I want to change that into a single pipe. So what must be the diameter of the single pipe? So imo kuha ng diameter ani. Considering usa ka head loss. Or it could be nga what will be the length of the pipe having the diameter of 300 mm. So imo na pong length sa pipe ina po imong kuhaon. So mo tong gingon ninyo ganina nga kani ang length ra ug ang diameter ang imong variable. So ani mo na maka-consider ka nga equal imong head loss 1, head loss 2, head loss 3 aning dapita dire. So for reservoir problems, here ang inyo yung kanunay timan-an ang kaninga junction P. This is the most important. You must locate junction P. Nganong imo mang i-locate? Kanang junction P diha ka mag-consider sa imong okay, so dili ka mo consider sa imong mga flow. So pasabot ana, di ba mao na imong junction? If you are going to put a piezometer here, mao na imong point ani. So kani nga point is imong i-connect ang tanan nga mga surface sa reservoir. So kay na-connected example kani ha, na-connected na ang imong mga surface sa reservoir kay bao na kas direction sa flow. Since this is ang kani nga point dire is padung ubos dire, meaning ang flow is with the direction ingani. If ang kaninga P is na dire, suppose, ato yung naon ha. If the P was supposed to be here, so mahitabo nga mura sa ingana. Kaning red, the flow will be ingani. Nakasabot no? So nganong na ingana? Tanawa ang imong unsa tong value, unsa tong EGL or HGL, the direction of the flow follows the slope. So asa ang slope dire? Padung ubos. Hala, nasayop lagi ni ba? Padong ubos. Yes. O, padong ubos ang slope ani. So, padong ubos ni. Ang imong slope diri is padong ubos. Di ba? Ang slope ani ni is padong ingana. So, imong direction sa flow is padong ingana. Ang imong slope ani is padong ubos gihapon diri. So, padong ubos ingana. So, if we consider ang kaning original, di ba? Ang sa tawag gingon, the direction of the flows follows the slope of the AGL HGL. So ang slope ani is paingana, so pa down siya, ingana nga direction. Ang slope ani is pa ingana, so pasaka siya pero the same direction. Di ba? Kay na possibility kita wa panay tanang mga linya dire injure ang gitan awang pipe. Ang usa ninyo nga mahog nga mahuna-hunaan is ang kaning si pipe B si kaning reservoir A ug si reservoir B nagsupply ni reservoir C. Pasabot na ho ana is katong unang drawing nga ba ang inyo pagtuki onan basin nga si B ug si A nagsupply ni C. Di ba mahog nga ana if wa pa mo ingani nga mga situation. Pero in reality, after solving everything, nakuha ninyo nga si ADI ang nag-supply ni B o ni C. Unsay usa ninyo nga timailhan nga na because of this junction. Diba? So, makonect ninyo nga na nakaibaw na mo sa flow sa padong. So, yan na siya. So, there are two types of reservoir problem. Oh, nakaday. Nakaho pa yung drawing kanina. So, kani dire, then napod dire. So, di ba, ang junction P is na deres ubos. So, yung flow is padong ubos dire. So, nahog nga, ang equation nga nakuha nimo is Q1 plus Q2 is equal to Q3. Dire, Q1 is equal to Q2 plus Q3. Si Q1 ra ang nag-supply ni Q2 o ni Q3. Dire, si Q1 o si Q2 nag-supply ni Q3. So, ingana na siya. So, types of reservoir problem. Okay, so given the discharge in one of the pipes or given the pressure at the junction P and the required is the elevation of one of the reservoir or the diameter over length of the pipes or given all the pipes properties and elevation of all reservoir, then you are to find the flow in each pipe. So kani ang duha. So balikon na ho sa kaning type 2 which is more common, gihatag tanan. Ang gipangayo is ang Q1, Q2 ug Q3. Ngano na trial and error because you have to check first if it is ingani nga flow or ingani nga flow. Whereas ang type 1 is gitagan kag usa ka Q, gitagan kag usa ka mga diameter, then ang gipangayo is either ang elevation, di ba? Or usa pod ka length sa mga pipe. So ingana ang mga problems kasagaran. So, procedure for type 1 with the known flow in one pipe leading to a flowing out from a reservoir, solve its head loss. So, mo dyan na yung kinaunahan, head loss. So, major head loss ra atong mga pangwaon ani. So, determine the elevation of the energy grade line at the junction of the pipe. So, see, you must know first the junction of the pipe, the elevation, so that you will know the direction of the flow. So if the known value is the pressure at P, the elevation of P prime is the elevation of P plus P pressure at the junction over gamma. So if you are going to draw the line, then you will know the direction of the discharge. So after that, you can solve for the discharge using the values and also the mga head loss nga formula. So, importante na dyan ang mga formula sa head loss dire. So, whereas dire, first you need to determine the direction of the flow. So most usually the highest reservoir always have an outflow, but ang middle reservoir is wata kibaw. So kaning B. Example kani, di ba? The direction of the flow B is mo rin na lahi. It goes up or it goes down. So mo na kasagaran. Not unless if there is a pump. Okay? So mahimo ng question mark if nanay pump kay pwede man nga si C ug si B nag-supply ni A na yung mga problem po ni ana. So kay na naman kay pump. So kung wa pa, so makasolve kay nga ni. So to find out the direction of flow in pipe 2, you have to assume nga wa kay Q2. So you will assume nga Q2 is equal to 0, then you make the assumption. So if Q1 is greater than Q3, then Q2 is towards B and P prime is above reservoir B. If Q1 is lesser than Q3, then Q2 is away from B and P prime is below reservoir B. So it's either kani or kani. Ang imong kinahanglan is you let Q2 equals 0. So muna siya. Then after determining the Q2, say towards B, express all the head loss in terms of X. So kana. Okay. So pipe networks, we will have that next meeting. So mao na ang sa imong reservoir problem. So mas masabtan ni siya next meeting. So next meeting we will discuss this. I will give you examples regarding this one. So karon ang gustong mangutana ko